Okay, we're going to be talking about random variables and distributions in this video. This corresponds to section 5.1 in the textbook. To motivate what we're trying to do in this chapter, let's think again about a dice roll. So our experiment, we'll be rolling 2 fair dice, and we're going to observe the sum of the dots that land face up. So for instance, if we roll once and we get a, whoops, didn't mean to do that. Roll once and we get a 2 and a 5, for instance, then the sum of those 2 dots means our random outcome that we're observing is 7, okay? So we can define this random variable to keep track of these random outcomes. So for every roll, we're going to record the sum of those dots. We typically denote a random variable with a capital letter, such as X, and it describes the individual outcomes of an experiment. Okay, so what we're doing here is where we're taking the sample space, which if you recall, since we have 2 dice and we have 6 outcomes for each one, we actually end up with 36 distinct outcomes. And what we do with our random variable is it assigns each of these outcomes to a sum, right? So if we have 2 and 2, right, that is going to be 4, 1 and 1 is 2, 2 and 1 is 3, and so on. So our questions then are, what does this tell us about the distribution of possible outcomes? So to do that, then we have to think about what kind of random variable it is. So a discrete random variable is one that takes on discrete or countable outcomes. This is an example of a discrete random variable because the distinct outcomes are ranging between 2, because the smallest sum that you can get is from 1 plus 1, which is 2, and 3, and 4, and 5, all the way up until 11 and 12, and then 12 is the largest possible outcome that is being measured here. Okay, so this assignment of the outcomes to a subset of the real numbers is the actual random variable, and when we assign it to a set of countable numbers, so integers, whole numbers, but in general just not decimal numbers, not numbers that have infinite precision. And that would be an example of so as opposed to continuous random variables, which would be doing things like taking measurements of heights and assigning that to an outcome. So let's think about a more concrete example. Okay, so let's say our example is an experiment in which we take a randomly selected person in the US, and we ask them if they have hypertension or not. Or we check if they have hypertension or not. So high blood pressure. The only kind of response that they can have is yes or no, right? So the outcomes themselves are yes and no. We're going to assume things like I don't know are not applicable here. So we can either say yes, they do have it, or no, they don't. And to each outcome, we assign then a number that represents this binary. So yes is going to be coded as a 1, and no is a 0. Okay, so x equals 1 means they do have hypertension, and x equals 0 means they don't. And because this partitions the sample space, right, then the probability of both happening together, they're independent and they're not independent, they're disjoint. So the probability of both of these outcomes should equal to 1. And so this is really important because this is actually how we're going to determine whether something has or is actually a distribution. So a distribution is going to be the random variable possible measurable outcomes which we also sometimes call the support. So in this example, 1 and 0, those are the measurable outcomes corresponding to do have hypertension and they don't have hypertension, together with the probabilities of each. So the probability of each outcome, right, whatever it might be, and we represent that as P of x equals lowercase x, or just simply, or P of little x, indicating that specific individual outcome. So when we are thinking about a distribution then, and we can set one up for the dice roll example. So remember that with the dice roll example, so the sum of the rolls, we can organize it like this. Take in each cell the sum of the row header and the column header. So 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, and so on, until you've filled out this table, which will give us all the possible outcomes. So you'll notice that there's a nice pattern here where then the patterns are repeating. So it's increasing by 1 as we go down the rows, and they're staggered as well, okay? So each distinct possible outcome is separated in bands. So these are all the different ways of getting a roll that gives you a sum of 9 or 10 or 11 or 12 or whatever. And now then we can form the distribution table where we take the probability that x takes on that specific value is going to be the number of outcomes in which x appears divided by the total number of outcomes. And this matches exactly what we talked about in a previous in the previous chapter. So we have our support of x and the probabilities. And when we set up this table, so how many ways can we get 2 from a dice roll? Well, we just count the number of 2s that appear in our table here. So there's just 1. So 1 out of 36. Actually, let me write that a little bit different so that we can settle everything in here. And then 2 out of 36, 3 out of 36, and so on. You'll notice that they're going up by 1 each time until we get to 7, which is the highest. That has the highest probability because there's more 7s than any other kind. And then we go back down again. So this is what we call the distribution table. And we'll know that we did this correctly if the sum of the probabilities, which we'll write as the sum over all the possible measurable outcomes, is equal to 1. So this makes this a valid probability distribution.